Hello everyone and welcome back, episode 24. Another guest episode, so we told you we're rolling with the guest episode, and this is Professor Andy Biggin. Because we normally have people on who are kind of from linked or very similar fields to us. However, as you said, you work in paleomagnetism. So I think for ourselves and for the listeners, what is paleomagnetism?
Andy, I've heard of this pole shifting, haven't we? And explain that to us.
So how often does this event tend to occur?
I said that reversals happen on average 4 times per million years or something. But if you go back 100 million years, there were no reversals at all for like 40 million years. One of the things that has changed as a consequence of that cooling is that the centre of the planet started to freeze. A billion years ago, or certainly...
It started to freeze.
Hello everyone and welcome back, episode 24, as Sam rudely drinks his Coke Zero. Tells me to bring it in, choose ice like ASMR. We're nearly at episode 25, big milestone that.
Episode 25, if we were a living human, we would be around our own age.
Another guest episode, so we told you we're rolling with the guest episode. So thank you very much for coming on and giving us your time. And this is Professor Andy Biggin. First professor.
Is it?
Yeah.
Wow. Well, congrats,
Thank
Andy.
you very
First
much
professor to land.
Wow. For gracing our presence.
Great honour.
I'm just trying to think, have we not had a professor?
No.
Is Malabar not a professor?
No, because he's more like, he does more of the programme leadership. He doesn't.
He lied to me.
Why
He told me. No,
Is that how he tells everyone to get them in? I'm a professor.
And we'll start with it now then, Andy. How would you, before we get into anything else, describe yourself?
So in work, I'm a researcher and, lecturer. Researchers in paleomagnetism. I don't know. Beyond that, proud father.
Okay.
Connoisseur of fine food.
How we start with all our episodes when we have guest episodes is we like to break the ice and ask a few highbrow questions. They're not really highbrow, but we like to say that makes us feel better. So the first one is, what is your favourite sandwich?
Okay.
The ultimate question.
So, I don't eat meat, right?
Okay.
So that's a constraining factor straight away. So I reckon...
Veggie or vegan?
Not even veggie, like I eat fish and...
just
like
not
pescatarian.
I don't like that. I hate that term, pescatarian.
Why?
It's such a nonsense label, you know?
Yeah.
It doesn't need a label, I just don't eat meat. But also it puts the emphasis on the fish as well, right? And the emphasis isn't on the fish, it's just,
you don't eat meat.
It's not like you're eating fish at every meal possible.
You got a thing like, no, the animals, no, but fish every day. I hate the fish every day. So what would you go for the filling then?
Right, so, this is it. There's been a bit of a revolution in kind of, fake meats and stuff recently. So that has been a massive
game changer.
Yeah, a big boom for me. So now I really enjoy like a fake and butty, I guess.
Are you onto the this isn't stuff? Is that what you're
that's what I was going with that, actually.
So good.
So bacon or even streaky bacon. That's a good one.
Where from?
This isn't.
Oh, do they do streaky bacon now?
Yeah, they do.
Oh, wow.
Yeah. And bit mushroom sandwich. Bit of ketchup.
Because you used to rave over the this isn't bacon.
Yeah, because I went veggie for a year, and I used to live on the this isn't stuff. So this isn't chicken, bacon, the sausages. That was just
quite pricey though, isn't it?
We had no money for a year.
But I was happy.
But I had no money, but it tasted nice.
So what are we saying then, Andy? Is it like white bread, brown bread?
Well, you see, I like my bread. I'm a bread
man.
So, me sort of artisan stuff.
Okay.
So, but then, it's a bit wasted in a sandwich, just have it with butter. But, I suppose the ultimate would be something like a sourdough or something from Kraft sourdough.
It's not wasted though. A nice sourdough, toasted, bit of butter. This isn't bacon. Doesn't need. It's the simple sandwiches. Bit of ketchup if you want it.
Do you want to say where does a really nice sourdough of all places? Lidl.
Yeah.
They have like a bakery in
they have at the back, don't they? Yeah.
Wow. I had it the other day. It was like £2 for a big loaf. And I was like,
that's pretty good. That's half the price of what I play down at Lutton Road.
If you ever get a chance, give it a try. It's really nice.
You can't beat though. Like, I know they have bakeries, but I feel like the Tesco bakeries, they're not as good. They're all done in batches. I feel like a proper bakery where you go and pay £10 for a loaf.
But it's so worth it though. It is so worth it. So is that what we're going for then? Faking sarnies on a toasted sourdough.
With mushrooms.
Mushrooms.
Tommy K.
Yeah.
I like it.
People who don't like... Do you like mushrooms?
No.
I'm indifferent.
Yeah, you're
like,
just
if they're on my plate, I'll eat them, but I'll never go, I have mushrooms.
Mushrooms are so tasty.
Yeah,
everyone tells me this.
And everything.
I do like a stuffed mushroom, like a portobello mushroom stuffed.
Thing is, with mushrooms, they soak up flavour so well, don't they, in any dish, lads? If you're in anything you put them in, they act like a bit of a meat. They soak loads in. So you're missing out, better.
I am missing out. I'll give them a try. But moving on to the next question.
Next one.
Is hosting a dinner party.
Right.
It's the famous question.
Yeah.
3 people, dead or alive, who we asking round.
Right. Okay. I've had a bit of a think about this one because I've seen it on your early ones. Right. I think some sort of god of science has got to be in there.
Okay.
And, could I get away with a couple like, Pierre and Marie Curie?
Go for it.
Okay.
Right, we've had people break the rules before, push the boundaries.
Yeah,
we'll take it.
Because Pierre,
that'd be so interesting.
Pierre Curie, he's foundational for magnetism for my own field. So I could bring him up to speed on developments in that field. And, maybe
this is what we've done since you've been away.
Yeah. He'd be so like forward thinking. He'd be like, I know, Andy. I knew this was
coming.
Andy, you just preaching to the crowd.
But yeah, Marie Curie was fantastic in discovery of X-rays and work on the radiation and so on. And as a couple, they won the Nobel Prize. So my partner's actually a geologist.
Okay.
So we could pick up some tips of how
to get in a Nobel laureate.
Yeah.
What have we got to do?
What are we missing? So who are the other 2?
Right. So you need some more funny, don't you?
You do.
But to keep the conversation going. And it can be someone dead, right? So I'm thinking maybe Caroline Ahern from the royal family. It's the daughter Denise.
Denise!
I know who it is.
Ahern. Her name's got an A in the front, hasn't it? It's like a silent A.
Sorry, was I not very clear?
Yeah.
There we go. Yeah, she'd be class.
She died.
She was on Gogglebox as well, wasn't she? Did she do the voice on Gogglebox? I'm sure.
Oh yeah, maybe in the early days, like.
So you're a fan of the royal family then?
Yeah, I am.
It's so funny.
The royal family. Man.
I tell you what, for years I always said no, I'm not really into it. I wasn't really a fan, and then my girlfriend, she was just like, no, you're watching the royal family from start, and then at the end, I was just like, I was in tears laughing.
Baby David, is eating dead healthy now?
What's
he on? He's got tomato crisp. He's dead healthy.
She's a vegetarian. She can still have an ham butty though.
Well, when Denise is moving out with her husband Dave for the first time, and she goes, "Just want to let you know, Mum, we won't be eating chips when we move out." And Jim Rowe goes, "You're not having chips? What are you going to eat?" She goes, "We're going to be having stuff like pasta." Bloody pasta! Where are you getting that from? And then it goes ballistic.
Wow, you've got that down, haven't you? Jim Royal.
I love
he's
the
class as
royal
that
family,
Jim Royal. He's so funny, so funny.
I love the Christmas episode where it's just been Christmas and like Barb comes in and he goes, "Barbara, don't want anything rich for me to eat tonight after all that food. I'll just have a couple of eggs on toast or something." He's just had his Christmas dinner. He goes, "Don't be going all out for me, girl. Eggs on toast will do." It's just, you can't beat it. No, that's a good pick.
It's a great second pick.
Denise's speciality is dairy on toast as well, isn't it?
Yeah. Dairy on toast.
For dinner. Yeah.
Funny.
So let's round that off. So we got the 3. Who's the final seat?
Right, okay. So I might go sport with this.
Okay.
So I don't watch very much sport these days, but I was a big Leeds Rhinos fan. Rugby league. And so, I've got a couple of heroes from that.
Okay.
From like the era sort of the, like 10, 20 years ago when, you used to go to a lot of matches. Yeah. So there's a guy called Rob Birrow. You might have heard of. He's got motor neuron disease.
So sad. Have you seen it?
Yeah, lads.
So sad. So sad.
So he's, he was a hero on the field, like.
He was such a good player, wasn't he?
Yeah, so he's dead little. He's like 5'5", He just used to run rings around all the big fellas. And then, and I saw him score, like at Old Trafford, I saw him score one of the greatest ever solo tries in a grand final. That was, so that was kind of special for me.
Is he the guy? I mean, I'm not big on rugby. Was he recently on the news where his mate was doing the
marathon?
Exactly.
Carried him over the line.
So I'm angling for another kind of pair here, because there's his best mate is like Kevin Sinfield, who was who's also kind of won awards for all his charity fundraising as well. So he carried Rob over the line after
that was so much.
7 ultramarathons in 7 days or something.
I watched it and I couldn't. I was when you're like,
you can feel it.
You lose your breath because you're getting taken away. I was like, oh, he's done that for his mate, man, and just like,
so sad,
it was
so sad.
Yeah,
you know what? I like that. That could be one of my favourite.
Little round tables, that your favourite? We've had some mad ones, haven't we?
We've had some good ones.
Everyone seems to pick Jesus, don't they?
Yeah.
Everyone loves having Jesus at the table. And then he's argued he's real, I've argued he's not real.
No,
so then,
because the thing is that there's a lot of things.
People say that he was real.
There was a man definitely there called Jesus. So I just put down, as I said at the time, 1 bottle of water and 1 dinner.
That's it. You're gonna prove this.
Right, we're getting to the bottom of this right now. But yeah, so that would be that. And then the final question we ask all our guests is, what was the worst job that you've ever had?
Oh, some belters.
The worst role. Where if you got offered to go back tomorrow, you'd be saying, I need a lot of money to go back.
Well, my first job. So, like my granddad lied about his age to go and fight the Third Reich. In World War II. I lied about my age to get a job doing a quick save. Which is like, it's kind of the proto Aldi or something.
I remember them. The ones with the white storefronts.
The red.
No, it was red.
Red.
Writing,
the quickie they were known as in Liverpool. Like on the quickie.
Oh, no.
So you lied to get in there, did you?
Yeah, I was 15 and I really wanted the £2 an hour or something job, so I lied about it. And I stayed there for a few years, kind of around doing my A-levels and everything.
Yeah, just money coming in. Was it bad though?
And it was really bad.
The quickie,
I just used to rock up hungover, like,
What was the worst thing that happened when you were there?
A little kid leaned out of a trolley and like pushed over a giant mound of glass jars of mayonnaise, and I had to clean it up. It was like, must have been about 40, 50 broken jars of mayonnaise.
Just a load of Hellmann's everywhere.
It was the good stuff as well. Like,
not the quick save zone. Proper Hellmann's gear on the floor.
What's class? Is that kid that been buzzing with himself, just like just like rolled away. Sat there devastated, like, oh no.
Well, I'll tell you what, the mum took herself away from there pretty quick.
Let's let this young A-level student clean it up.
Don't want to get stung for £2,000 bill for mayo.
The only thing I remember about the quick save is there was one by ours in Crocky, and I was going on holiday when I was like 10 years old, and my mum remember they used to have like the photo booths in like the porch of the shop, if you like, or whatever that area is called, and my mum like said, I'll wait in the car, I can see you, go and get yourself a passport photo. I was like 12, 10 or 12, and she went, go on, and she was on the phone, she was watching me, and I just went in, put my coin in, and instead of getting like a small print of like 10 photos back in the day, it's mad, you had to go to a thing to get one. I clicked A4 portrait and I was only 12, and I sat there and got a photo, and it come out, and I thought, what the fuck make for a passport? I went out to my mum and through the window I went, yeah, and she went, what the fuck's that? And I went, my passport photo, how are we going to get that on a passport, Sam? And I just went, I don't know. And then she went, come on, and got me and went in. But
that's class,
I remember, mad the way you said quick save, I remember
that is the most used story I think I've ever heard,
Yeah, man, still doing stuff like that to this day.
You are. So what we normally do when we have guests on is we always say, like, take us back, when did you first kind of get into your field? When did you first discover that this was the origin as like a passion? However, I think before we get to that, like, because we normally have people on who are kind of from linked or very similar fields to us. However, as you said, you work in paleomagnetism. So I think for ourselves and for the listeners, what is paleomagnetism?
Okay,
as the definition.
Yeah, it's the study of the magnetic field recorded in rocks, basically. Okay. And normally we're talking about Earth's magnetic field recorded in rocks, because most rocks are terrestrial from Earth. But you can have, lunar paleomagnetism. You can have meteorite paleomagnetism as well. So it is, it's just what it sounds like, ancient magnetism. So, most rocks, when they form, will lock in some sort of signature from the ambient magnetic field that they form in. So, and that's normally, on Earth, that's normally the Earth's magnetic field, because that kind of dominates over everything else.
And then you can kind of track how that changes through geological eras.
Yeah, so then it maps into geomagnetism, which is the study of Earth's magnetic field. And in particular, it's so the magnetic field's been around for a very long time, and it changes on timescales that are longer than human timescales. So our only chance of really understanding it is to look to the geological record, and these kind of we've got direct measurements going back a few centuries from mariners and things, but that's if you were to compare the magnetic field to the sort of climate system, then a few centuries, the magnetic field is like just a few weeks or something for the climate.
Very little happens.
So you can't you couldn't study the climate in just a few weeks of data. So you need these thousands and millions of years long records of the
so they almost hold like ancient transcriptions of the past, like almost information is interlocked in basically rocks.
Yeah, I mean
through magnetic fields,
and that's that's true about rocks in general. The whole field of geology is like using rocks to tell you about the ancient Earth. But the special thing about paleomagnetism is that it's telling you about the magnetic field, which has its origin in the Earth's core and is relatively unaffected in its passage from the Earth's core, 2,900 kilometers beneath our feet, all the way up to the surface. So it's like you're getting a record of what's going on in the deep interior of the Earth, and that isn't something that generally, geology can give you. It's only telling you about the surface processes.
So it gives you a more deeper understanding of what was going on right in the center of our planet, essentially.
Yeah, that's right.
So cool.
And to understand, the kind of evolution of our planet, then I think paleomagnetism is like essential.
You say it's the magnetism trapped in rocks. So what specifically are you looking for? In is it just the magnetic field that the rock gives off, essentially, or is there certain features?
Yeah, it is basically. So most rocks are magnetic to some degree, and because they've got tiny little magnetic particles in there. So, the most famous of them is called magnetite, and it's just an iron oxide, and it forms about 1%, of basalt, which is the most common rock on the Earth's surface. So underneath all the oceans is basalt, basically.
Okay.
And that 1% of that basalt is magnetite, which is really strongly magnetic, but just tiny little grains, because big grains are unstable. They don't record a reliable record. They will have their record constantly overprinted. Whereas really tiny ones, so we're talking, sub-micron here, more than thousands of a millimeter, less than that. They're the most stable.
Larger rocks are more unreliable because there's
larger grains within the rocks.
Larger grains are more unreliable.
Yeah.
We've just had a grain expert on, haven't we? Dr. James Baker.
Yeah, in like granular flows. And that was his expertise, and how things
grains
move.
compact, on volcanoes and
like
stuff.
volcanoes and like
rock
emergency stuff and that. So very similar. Like it's weird.
No, sorry.
Sorry,
it's
it's a bit. I guess rocks are granular on all these different levels. So it's it's like fundamentally rocks are collections of minerals, which form themselves into what we call the grains or the crystals. So they've got to be small to be a reliable recorder.
Makes sense.
What is then, Andy, for you, like, what is the most important thing that paleomagnetism brings us about possibly making predictions about the future or looking into the past? What is the most important application of it It might not be the stuff you do, or is it the stuff you do? I don't know.
Well, it's related to the stuff I do, yeah. So as I said, the magnetic field is always changing, right?
Yeah.
And it does change a bit on human timescales, you know. So if you're into hiking at all and you want your compass to be, you know, dead accurate, then, you know, every few years or so you should slightly modify it, because magnetic north will have moved relative to geographic north, right? So it's doing these small changes all the time, and most of the time, you know, magnetic north is near geographic north, right? And it's sort of just dancing around. But then every now and again, this, what we call this secular variation, this just sort of wobble of the magnetic field, it gets out of hand, and the field can collapse altogether. And you might have heard of magnetic reversals. The polarity flips. Yeah, that's right. Yeah. So that's the most extreme example of that then, that the field becomes so chaotic that then when it rebuilds, it forgets which polarity it was originally in, and it just grows back in the reverse polarity, and then it gets stuck.
Well, Andy, I've heard of this pole shifting, haven't we? And explain that to us.
So how often does this event tend to occur?
Right. So it's good that you said tend to occur, because it's not regular. Yeah. So we can't predict when the next one's going to happen for sure until it's nearly on us, right? But
is that dangerous?
I'll come back to that. But yeah,
if you can't predict it, that sounds pretty dangerous.
But it's quite slow, so we would get some warning when it happened. Might be able to adapt. Yeah. So the last one happened 780,000 years ago.
Right.
But on average, in the last 10 million years or so, they've happened about 4 times per million years. Right. So you could say we're well overdue, but you know that doesn't mean that, you know, one's going to happen very soon. It could be millions of years before the next one happens, because it's just a stochastic process. Just don't know.
So has there ever been, I suppose this is a proper mad question, of like when it collapses that it rebuilds in the correct way? Like, so for example, every time it collapses, does it always flip, or can it rebuild the correct way?
In fact, more often than not, it comes back in the same polarity it was. It recovers. So we call those events excursions. Right. So magnetic excursions. So there, the pole, the magnetic pole, goes a long way away from the geographic pole. So, you know, more than 45 degrees, so it's near the equator somewhere. Yeah. But then it recovers again. And those tend to be a bit short-lived events, so they might only, you know, big one of those might only last a few thousand years, whereas for your full reversal to happen, that can take, more like 10,000 years for that to happen.
To fully
reverse, to go from being stable, normal to stable.
And how long did you say it takes to go from the equator back up to where it was originally?
Well, so the field becomes, you know, very complex at these times. So it's no longer well described by a simple bar magnet, you know, which is how we tend to think about it.
With the two things coming like
exactly
round.
The flux lines, going from pole to pole. So that's not a bad description for the field today. But at times when it's undergoing these excursions or reversal transitions, it's much more complex than that. So it's multipolar, and you get so that means that the pole that you're, you know, closest to you that you're seeing might move very quickly indeed, you know. So we've had arguments that there's, you know, from high resolution lake sediments and stuff, had arguments that you can see, you know, it happening within decades, you know, the kind of this thing moving over. But that will probably be in just that one place, you know, where they've caught it, and other places would not see such rapid changes.
That's insane.
Wow.
So I know. So basically, I was just going to ask the question you referred to
go on.
before. What are the implicit dangers now? Because obviously, when this has happened in the past, we've not had things such as electricity and things like that. So, what are kind of, and human life as we know it? So, what are the dangers then? Should this happen today?
So, the magnetic field does a big service for society in kind of shielding near Earth space from solar wind radiation. Okay, so we're talking about 10 Earth radii, so 60 odd thousand kilometers above the Earth's surface. you've got the magnetic field goes out and kind of dominates near Earth space in that side, and then it hits the magnetic field because it's coming from the sun, basically. And that magnetic field's being carried out on a stream of charged particles. And there's nasty stuff, these charged particles, There's, have you heard of solar storms and things like that?
Yeah.
So, if you had an astronaut that was outside the Earth's magnetic field, on the moon or something during a very big event, and that could potentially be lethal.
Wow.
The amount of radiation they received. So the magnetic field does a great job of
blocking out that
radiation.
radiation,
Basically
if you like.
deflecting that radiation around the Earth.
And is that what causes the northern lights and
it
stuff?
Is
that
so
what
that's the
causes
stuff
that
coming in actually, because
Right.
as you just said, those flux lines, they come into the Earth, right? So at high latitudes, the stuff it's like it gets stretched with an elastic band. This at the night side of the Earth, so the side away from the sun, and then it kind of pings back, and then these particles come in at high velocity, then hit the atmosphere. The atmosphere is a very good shield as well for the solar radiation, but that's what creates the lighting effects that are aurora.
Wow, this is all, sorry, there's loads of things in my life connecting all of a sudden.
So obviously then the danger be once it flipped, the magnetic field isn't so much there or provides the same level of protection. Is that kind of the idea?
That's right. And well, it's worse than that maybe, because it becomes all complex. So it might actually be driving the solar wind into the atmosphere at low latitudes as well. Which is where there's more life tends to be there. Now, so it's dangerous. We've got no evidence that life has suffered during these magnetic reversals in the past. Although someone did publish quite a controversial thing about Neanderthals going extinct in a quite high-profile paper, actually, because of the last big excursion, actually. So,
but weren't Neanderthals still about, though? Like 70,000 years
no,
ago?
this is 40,000 years ago when the last big excursion happened.
Okay.
It's called the Le Champ excursion. But that's pretty controversial. In general, we don't see any records in the in the paleontological record of like life suffering during these reversals, because there's been a lot of them. 4 per million years. That's quite frequent in geological time. So life has found a way to adapt, and things like the birds that use this that use magnetic field for navigation. There's even been studies suggesting that they're able to recalibrate their internal magnetic compasses using the rising and the setting of the sun, so that they
birds
can...
are fascinating, man.
So they can...
Life's just fascinating in general, isn't it? Like how this type of stuff can just...
So,
occur.
what are the indicators, Andy, to a polar shift happening?
Yeah, so the field will get much weaker, and it has been getting weaker for the last few centuries. So, yes, it would come, but it's still quite strong by geological standards. But it would keep on getting weaker, and there's a funny region of the Earth's surface, magnetic field at the moment, called the South Atlantic Anomaly. And that's getting bigger at the moment. So that's kind of causing the global field to get weaker, that we've got this sort of anomalous. It's like the field's pointing in the wrong direction, actually. Down in at the core mantle boundary, and so that sort of anomalies like that would grow, and the field would just become more complicated, and
then you might get people saying we're on the edge of possibly moving into
this is all going to take. This probably all takes centuries though, so it'll be played out in quite slow motion.
I'll be dead. I'd sound.
So
it
would be.
There's no evidence that it causes major issues anyway.
Oh, yeah.
There's a much more immediate related threat, which is from solar storms themselves, because they essentially, if you get a very weird bundle of the sun's magnetic field coming out to the Earth's magnetic field, it can kind of open it up like a tin opener, and then all this magnetic flux can get inside, and you get aurora at very low latitudes. But you'd also, get potentially a lot of damage to electrical infrastructure. So,
it's not going to be the ozone layer all over again, is it?
Well, in the 19th century, there's something called the Carrington event, right?
Yeah.
Which was a very big solar storm, and that did cause all these electrical problems in these telegraph lines, right? But that was something when technology was very, very nascent, right? If it happened now, it was predicted. This is a few years ago. I think we're better prepared now, but only, I don't know, 10 years ago or something, the National Academy of Sciences in the US predicted it would cost us like $1 trillion or something.
To recover from such an event.
Yeah, because the problem is if it knocks out transformers, right, in the power grid, then they're not quickly replaced. So that means a big area of the grid goes down, and then, you know, you're trying to replace that, but, you know, you can't because you haven't got any power to power anything, you know, So if it was a really big one, it could sort of cascade down and, you know, be very problematic.
The amount of like social media flies who live on the phones who couldn't get it charged.
They just sit there with the phone, just looking at the screen, swiping up,
crying their eyes out.
Well, that's right. We're so reliant on it, and GPS, would potentially go down as well. You know, you could have a lot of satellites like losing function. So, and GPS is used for all sorts of things in, you know, agriculture. For example, you know, so it's so it did feel like 10 years ago when I was teaching this in a geohazards module at Liverpool, I felt like we weren't very prepared, and now it does feel like the governments are starting to
wise up to this, maybe,
and be ready. I mean, ultimately, you know, you could be safe just by shutting down power grids just while the storm is going on,
because there's nothing active for it to kind of break, essentially.
Yeah, that's right. It's all about, it adds. So you've got power flowing through these lines, and they've got thresholds that, you know, the transformers can cope with. Right, you don't want to add anything massive to it. So if you just shut it down, then
you know what?
Then it's built-in protection.
I don't trust that the government's ready for that. And apparently we're ready for a pandemic, weren't we?
Yeah. Well, there is that.
We're ready. We're ready for the polar shift. 6 months later, we're all fucking locked down somewhere.
Tell you what, though,
the poles have shifted.
It is crazy, and how just like one day the sun could just go, right, you're not having telly anymore.
Yeah.
There we go.
No royal family this week.
It doesn't matter what you do, the sun just.
That's it.
So I suppose then, so now we've gone into paleomagnetism a bit. How did you first become like, this is my subject? How did that come about?
Yeah, I guess it was choosing my PhD.
Was that when you first kind of were?
Yeah, well, I actually did an undergraduate project in my last year, which was in paleomagnetism, and I enjoyed it. You know, it involved a bit of field work and a bit of lab measurement, and it told us something about. It tells us about how continents move around as paleomagnetism. You know, it's one of the. You'll be familiar with the basic idea of plate tectonics.
Yeah.
Or like the story of like Pangaea and.
Yeah, that's right. So basically, you know, the proof of that really came from paleomagnetism back in the. You know, from the 50s through the next few decades. So because the magnetic field looks different at the poles as it does at the equator. Yeah. So you can see you can tell that continents have changed latitudes. You know.
Because the magnet, like how the residue in the rocks looks isn't how it should be for where it currently is now.
That's right, exactly. So the direction changes. So, you know, if you've got something, let's say, that's close to the equator, or in the northern hemisphere, slightly like India, you know, so the magnetic field there today is pointing kind of quite shallow northward and down, right? And you got these rocks, you know, from 50, 60 million years ago, and it's pointing up and much steeper. Yeah. So it's like, well, that's what it would be like if it was in the southern hemisphere, you know, fairly mid latitudes. Right. So the inference being that, you know, that continent has rifted off.
It must have been here previously due to the nature of how this place looks now. Is that how you connect them?
From the magnetic field direction. Yeah.
Wow.
So so I was doing that as my undergraduate project on the Isle of Man, and some rocks there that are about 450 million years old or something. And I quite enjoyed that. And then, you know, I was just looking for something to do, and my
don't want to go back to Quicksave.
I was quite fortunate that this a guy who used to be a PhD student and a postdoc at Liverpool had just set up a new lab in Kingston University in Surrey, and he was looking for a PhD student, and so I applied for that, and and took it from there. And I think what really appealed to me about that project, well, one thing, it had field work in Australia, so that was quite nice. But also, it was trying to tackle, rather than just, kind of looking at the how things moved on the surface of the Earth, this was dealing with, the kind of the deep interior of the planet and how things have changed in the planet's core. So not just looking at the direction of the magnetic field, but looking at the strength of the magnetic field, which is much more difficult to recover, actually.
Yeah.
And that's basically what my lab specialises in today.
Okay.
Is measuring the ancient strength of the field. Yeah.
Wow. Okay. So what about in Australia? Did you?
Whereabouts?
Yeah.
So it's pretty broad ranging, actually. So we went as far south as Kiama, which is not far from Canberra. It's on the east coast, and then all up the east coast up to Cairns, like on the Queensland. So basically, we did 2 big road trips.
Why does this make our PhD sound shit?
But we just sit in front of computers.
Right.
But don't see what's
We
magic.
are fucking lame, man.
I say this all the time, right? We're data scientists, right? All I need is that laptop to do my work, and I choose to do it at home. I could be
uninspiring
anywhere.
is that?
Anywhere in the world.
So uninspiring,
Choose
man.
to do it in bed.
Looking at your mother while you do it.
Yeah, it's
Do you
like,
know what I mean?
Mum, do you want a brew? But yeah,
Who have spoke to other professors, doctors, and everyone's PhD sounds so much more exciting.
Like we had
Just
James on the other week.
Yeah.
I just worked in Australia for a bit. Then I was round here. Then we had Dr. Ivo Seatman on. He was like, New Zealand, Australia, just all around. And then we're just like,
Data science
Liverpool.
it attaches you to one of those.
It does,
things, man.
Yeah, but it's just us. We keep ourselves grounded at home.
Humble.
So you said you worked in Australia. We also saw when we were reading your profile
Get
on
some questions.
the uni off that you've been in Mexico.
Yes.
Mexico and in Central Europe. Like France.
Montpellier.
Yeah. So I suppose the question is then, so obviously, what were other than obviously the magnetic field differences between the 2 places, was there anything else that the different geolocations kind of showed up in
that's a good
in the
question.
rocks?
But no, it's got quite a boring answer, really. It's where the money was. It's like,
You cop out.
So, in Mexico, I didn't really get to do much field work in Mexico, actually. So my then supervisor went off on sabbatical straight away. So, I was kind of left trying to set up the lab because the lab wasn't quite working properly.
Okay.
And then actually, we had a limited success there. And then I got into, the more sort of theoretical side, numerical side, because that was something that, I could do with just a computer, right?
Yeah.
So Mexico, I had a fantastic time there, really, wonderful event. But I didn't, some great holidays and stuff, but I didn't really make the most of the geology. Actually.
Progress was limited.
To be
Fun was hard.
To be fair, I'd be like that if I was in Australia and Mexico. I'd be like, well, this is brilliant.
Yeah.
No, it's different. So for field, Australia was field work. That was going and collecting rock samples.
Yeah.
And I've done that in many different areas of the world, including a little bit in Mexico, but I didn't do it much in Mexico.
Yeah.
And didn't do it much in south of France either, because that was working on samples that had already been collected. I was only there for a year, but then I went to Utrecht in Holland after that, and that was the making of me. I'd say that was really
Really involved.
great lab there, and I did lots of field work there in South Africa and Turkey. I'm working on very different age rocks. So in South Africa, it was some of the oldest rocks on the planet. Actually, it's absolutely extraordinary. 3.5 billion year old rocks
In South Africa?
That look just like you can go to rocks that are relatively recent in geological terms, in like Wales and see
And it
look
all looks
exactly the
the
same. Yeah, it's extraordinary.
It's wild.
Are we talking, this might sound like a stupid question, are we talking particles or are we talking like...
No,
The
big
actual rock.
rocks.
Big
So you
rock.
can see. So if you've ever seen a video of a mid-ocean ridge, you see the hydrothermal vents and stuff. You see the lava coming out and then immediately cooling down because it's in freezing water, right? And they form these lobes that they call pillows. Right? So you can go to Barberton Greenstone Belt, it's called in South Africa, and you can see pillows just like that. that formed in an ocean 3.5 billion years ago.
Isn't the world
You
only
see
like
little-
4 billion years?
4.5, yeah.
That's wild.
Yeah.
So essentially,
these
that
are
was
some of the oldest rocks.
that was like when the Earth was like properly starting to cool down. Essentially, where we could would that be one
Wow,
of the first
cool.
instances?
Or
of
were we
that?
still
This
under
is,
bombardment or whatever they call it?
Yeah, that's a very controversial question. Whether, to what extent the Earth resembled, today's Earth back then. These rocks certainly look like rocks that can be found on Earth today. But the argument could be that we were just lucky, and that was just one place that is where was retained such rocks, and actually
because there's a small sample. It's not really. You can't really. It's not inducive to the whole kind of this is what it was.
Yeah,
type thing.
I mean, there's a lot of granites around there, and granites are these lighter coloured rocks. They form when you melt the darker coloured rocks that are in the oceans, right? These basalts and things, right? So if you've got that, then that suggests that you've got the original rocks, these basalts that are going down into subduction zones, and then being remelted and making these granites, right? So that suggests that you have got a process like what's going on Earth today, plate tectonics and so on. But some people think, no, it's, that's just a very local thing, and actually you didn't have plate tectonics for perhaps another billion years or something, and that the Earth was very different. But almost certainly you had less continental crust back then than you do today.
Wow. Yeah. So this is more or less. That's insane, isn't it? It's unimaginable.
I can't get my head around, because I know about like the bombardment the Earth went under. And like 3 billion, it must have been, as you say. So it's controversy of, was it actually cooling and what it looks like now, or was it still in that period? But I just can't get my head around how something's 3 billion years
and you can
old.
just go and see it.
That rock has just been like that for 3 billion years.
And it must have been protected.
It must chilling, just like it's happening.
So it must have been protected in the for all that time as well, because otherwise obviously it'd have been eroded away.
Yeah.
Like. But as you drive into this mountain land, it's really funny because you're on this flat land, all across for hundreds of miles across South Africa, and then you drop down into this region, and it's like you're dropping down through these rocks that are protecting these older rocks, and then you get the access to like the basement and this proper old stuff. Yeah.
So a question again, probably away from rocks. So you've worked the place from like in places all over the world. What's kind of like the academic culture? Is it like how does it differ in different places of the world compared to how obviously we have experienced it over here in little old England? Yeah,
so it is subtly different in different places for sure. So in Mexico, the academics had a pretty good life, got to say. Very well paid. Tend to live in big houses with staff and
Really? Yeah. He's called Mexico.
Seriously?
Not permanent servants, but kind of gardeners and and maids and things, and
paid for privately or paid for by?
No, just
because they get
well
a
off
decent
because
wage.
of that. Well, that's what I'm saying. Yeah.
But football pitches in the gardens.
Shut up.
Seriously, it's like some very nice. And the culture's very relaxed. So go around each other's houses. Have nice dinner parties,
Play footy
every week. Play footy with the kids
in the garden.
That's right. Yeah.
Wow,
that's insane.
So that was quite decadent, really. And then in France, so there I think it's I think UK is quite extreme in sort of like the PhDs are relatively cheap for the taxpayer to cover, or whoever it is that's covering them. So there's a lot of them, right? And few go on to academic positions, right? Whereas, it's a small proportion, unfortunately. And then, whereas in France, it is like, I've heard it said that, some people, they won't take on PhD students unless they know there's going to be a job for them, like as a lecturer, down the line, because that's the sort of career track.
Wow.
If you do it, so and then Utrecht is a bit more, I guess, like
Similar.
the UK. But then still, you do 2-year masters, and then 4-year bachelors, 2-year masters. the second year of your masters is basically a
project.
PhD. Is like first year of first year of PhD, and then you got 5 years for your PhD. So it's
Where's
like
this?
Utrecht, but I think it's
Netherlands, sorry.
yeah, but I think it's like that, in large parts of Europe, and to some extent in the US as well. I got my PhD at 24. And that's that's completely unheard of.
Did you go straight from undergrad to PhD?
Miss your
Well,
masters,
I always say this. I've said this to you. I've said it to a few people. I wish I had more time in my formative undergraduate and masters years, because a lot of the time I feel it's very pressured in the UK to learn, get right. I'd love to have just had time to read and write and do all the other things. I'd delve into a topic instead of it just being. Right, you've got an assessment. You've got an assessment in 2 months, type thing. Yeah, so that in the Netherlands model, that sounds like I've been wow, that's class.
Well, also, I've heard it, said that the male brain in particular is not fully mature until 26, right?
Tell me about it.
Yeah, I think I was definitely living proof of that. But so it's like it's hard to then be at that level of training of specialism, really. When he's so young, and I think that if you're in somewhere that nurtures you a bit more
and allowed you to mature with the subject kind of more slowly and more naturally, instead of it being right, you've just got to get through as a function to either be a lecturer, or the small people go on to it, or just go and get a job and be productive.
And as you say, in the UK, 90% of people who do PhDs just don't go into academia.
Yeah,
they just get off.
Plethora of reasons.
Either because there's not enough jobs, or they just, as you say, job security, but I think there just isn't enough positions. So you take them on. There's loads of these doctors working for big private industry firms who just moved on because they couldn't pursue what they wanted to do.
It's a shame the brain drain essentially from academia, isn't it?
Yeah,
that goes behind closed doors.
I mean, it's brutal, right? Because it means that you've got to, if you want an academic career, well, you either have to be extremely lucky, or you've got to be prepared to kind of
jump ship,
to move all over the place, right? And just take whatever's available until you find
a place where you can
when the right job comes up,
that's it. So I was going to ask then, Andy, what you hit on a little bit about what your lab specialises in. What exactly does your lab specialise in the umbrella term of paleomagnetism? What research do you guys specifically do? What are you doing at the moment?
Yeah, so we work across the whole field of paleomagnetism. So right from the very small to the very large.
Okay.
So and theoretical and empirical as well. So we've got some real not me, but we've got some very talented individuals in our group who work on something called micromagnetics. So that's essentially simulating at this this very fine scale of millionths of a meter, the changes in magnetic structure within these particles. So that's really trying to explain how these particles have such stability, how they're able to hold on to the magnetic signal for billions of years,
long,
right? And then we go out and we get rocks and we measure them in the lab. So we do a lot of that. So we've got a lot of good equipment for measuring that. So very sensitive magnetometers. So
you go get them yourselves. It's not like you just go and retrieve.
We do it.
Well,
see, this is the thing. This is a reason that I really got into research. Actually, that I decided I wanted to trade. Well, no, it was the whole thing, the whole package from start to finish.
How you can see getting something from the ground outside and then taking it through the whole process and this is the result.
Yeah, and then writing up and presenting that result. Because if you work in the private sector or something, often they make these processes more efficient by having individuals specialise in just one part of the whole process, right? Whereas, in academic research, you kind of have to take charge of the whole thing and do it from start to finish.
I suppose that's more interesting. It keeps it fresh, doesn't it, what you're doing?
I think so. Yeah.
I agree, yeah.
I really like the variation, though. So sometimes, I'm there,
It keeps you... Sorry, I want to get back to what your lab does, but just hitting on that question.
Yeah.
It keeps the this is just my opinion as well, but like, for example, we're data scientists, and if we feel like we've been trained to, like, we just get the data, we don't know where we know where it's come from, it's been collected by someone else, it's been processed, and we get it, we analyze it, and then we'll like pass the results on to someone who can like interpret it. But I feel like from start, and then obviously certain fields, it's hard to do in like healthcare. You're not going to go and collect loads of information on a patient. Exactly. But just sort of the point I was making is, it feels a lot more like authentic coming from you as an individual or the lab, because you have carried this like baby, if you like, through its process. It's not been, you know, dissolved or like sanitized by everyone getting their hands on the project and going, well, we've done process the data this way, we feel like you should do that with it, okay, we're going to analyze it, okay, now we're going to pass it on and they're going to tell us about the result. It's all, no, this is our baby and this is what we've done it how we wanted to do it, not how everyone else got the stinking paws on it.
But that's got part of the problem in there as well, though, because if it is your baby, you're taking it through from start to finish,
you're biased.
You might be biased. It hasn't got the checks and balances in the, you know, in something like analysing health statistics or something. You know, you don't want just
it's but you see what I'm saying? It's got the trade-off. It's like, I hate when everyone gets the mitts on stuff. I just feel like it ruins it. It's like, stop ruining what we're doing. Get your damn paws off my shit. No, but your lab.
So we've got magnetometers. So one of them's very nice. You know, it basically is. It's like a piece of factory machinery or something. It's automated, so you load your specimens on there, and it kind of picks them up with a robotic arm and does the experiment for you. And and at the heart of that is a cryogenic magnetometer. So it's the most sensitive magnetometer that we have. They don't operate at room temperature. They've got to be the superconducting.
So they 0 Kelvin or as
close to so below 4 Kelvin. So that's, that's just, you know,
still very cold.
Minus 270
still very cold.
So we've got we have to liquefy helium to do all that. And so we've got a few of those, and then and then we go right up to sort of some of what I do is collaborate with mathematicians on simulating the processes of fluid flow within the core, and the dynamo process that produces. So it's making computer models of what we call the geodynamo, which is the thing that makes the Earth's magnetic field.
So this be like mathematical systems with it, like of what type of equations?
So it's Newton's second law. Okay. So essentially, but in terms of the Navier-Stokes equation, so fluid flow.
It's all fluid dynamics.
So it's fluid dynamics, and then but then linked to, obviously you've got then the Maxwell's equations for the electromagnetism as well. Which then feeds back into the fluid flow as well. So it's pretty complex, and I don't write these programs. I take ready-made ones, and but I do get to play with them. You know, it's quite good. So I get to change the inputs and then run them on. So I'm running stuff at the moment on what's called Archer 2, which is the National Environmental Science supercomputer framework. So it's what they use for the big
to do the big calculations.
So it's what they use for the big climate simulations, you know, that you see in like IPCC reports and stuff like that. So we're just using a part of that for simulating the core and trying to make it look like the Earth did, you know, along the Earth's magnetic field looked
based
a long
on the
time
findings
ago.
from the rocks you found.
Wow. So you know, I've moved into that area because I really enjoy it, and I've been really fortunate in finding great collaborators as well.
Wow. So a question that's just kind of came to me then is, obviously we're data scientists. We work with like machine learning, artificial intelligence, AI, the buzzword as everyone uses it. Does that play like those type of techniques? Are you leveraging them in your field? Or
I am not personally, but yes, the other guys, my group. So they run these micromagnetic simulations, and they're interested. You know, so they'll take a grain of magnetite, you know, and simulate in all these different shapes, you know, and then they want to try and match up with the observations then and try and infer, you know, to what grains, the assemblages of grains are. So we're talking about millions of simulations there. So machine learning then is really
makes sense.
The complete makes sense to try and learn which are the best
because it makes sense when you get past so many data points. It's unfeasible.
Trying to hand
trying
a
to
billion data
hand.
points to a logistic regression model.
Or just trying to
mini
eyeball
tab.
it.
Yeah, Minitab.
Everyone knows Minitab.
I haven't used that for 20 years or something.
And there's a reason, because it's terrible.
I remember getting mad confused about Minitab when I first got given it.
And then the first thing,
first year, I was like,
someone goes, "It's not Excel," and you go, "Well, why is it like Excel then?"
This is Excel.
This is Excel. Stop telling me it's not.
So,
I've had enough.
Andy, what is then the main? Like you were saying, there's a group doing micromagnetism. Is that what they called it? What is the main of the lab, or of your specific research, what you've just described? I'm getting, and I'm sure there's people going to be listening. What's the main it doesn't need to have one either. Application. What is the an application? What is the main thing you're trying to?
No, there's a big theme.
The umbrella thing. Exactly.
That I'm interested in, and I've been my whole career, and that's basically using paleomagnetic records to tell us about how the deep interior of the Earth has changed over millions to billions of years, right? So Earth is not just a rock, right? It's obviously you've got all the life at the surface, but even inside and its interior, it is an evolving thing, right? So you've got an outer core that is liquid, and then a mantle which is solid rock, but that rock is moving, right? It's flowing just like a very, very viscous liquid, okay, over millions of years, right? And the whole Earth is cooling down, right? It loses 44 terawatts at the moment is the heat that's been released at the surface.
Is that expelled through things like the volcanoes and underwater volcanoes?
Yes, exactly.
That
nearly all of it, is concentrated at the mid-ocean ridges.
Yeah.
Okay. That's right. That's where the heat's released. So that's a lot of heat over geological time, right? Because now partly the planet keeps itself topped up in heat by because it's got radioactive minerals in its interior. Okay, and there's elements like uranium, thorium, potassium, which are decaying, which are keeping the planet hot. But actually, that's only part of it. Most of the heat is still heat that's trapped in from the original accretion of the planet 4.5 billion
the original
years
creation
ago.
of the compaction of it with impact. Wow.
That's right, yeah. So it's still trying to lose that heat that it's got, and that's causing it to evolve through time. So one of the things that has changed as the consequence of that cooling is that the center of the planet started to freeze. Okay, so 1 billion years ago, or certainly
it's started to freeze.
Yeah. So the inner core is bits of the outer core that have frozen at the center of the Earth. Yeah, and it's not because it's cold; it's because the pressure's so high. But then when the temperature drops, then it changes to the iron freezes in the center. But then the core isn't all iron, right? It's about 20% lighter stuff. We're not entirely sure what it is, but silicon, sulfur, oxygen, that sort of stuff.
Just lighter elements.
Yeah, lighter elements. And they do not get frozen in with the iron. So the iron goes into the solid ball at the center, the inner core. The lighter stuff is then free to float up to the surface, right? And it's that is what is driving then the motion in the core, which is what is generating the Earth's magnetic field. Okay, so you have to generating a magnetic through a dynamo process, just like making your light come on your bike by keeping your pedals turning. It takes work, right? So that work has got to come from somewhere, and it comes in large part, we think, by the inner core, growing and releasing these light elements. So, one thing that we could learn, that one of the big research questions that we're trying to tackle is, when was that precise moment when the first iron froze at the center of the core, right? Because that will have been a major power boost to the magnetic field, because suddenly you're releasing all these light elements that you weren't doing before. Okay, so we're looking
strength in the field, essentially.
Yeah. So we're looking for that signal of inner core nucleation, and if we had that, then that would give us, because we've got all these models of how the Earth's been cooling down since its history. Yeah. They're completely unconstrained. They're just based on what we see today, and then you just go backwards, right?
Just extrapolate in reverse.
Yeah, and all sorts. So it's So these models are just very, very poorly constrained.
Actually, like assuming linearity in how it kind of things, and
Yes.
very oversimplified, but like obviously not taking into account there could be a big dip here or a big increase or something elsewhere. Like
And just, the only constraints you got rocks on the surface that are up to, maybe 3.8 billion years old. So you know that the surface has been solid since then, right? Apart from that, you haven't got much going, some chemical indicators and stuff. But, the magnetic field, we can say that the magnetic field has been going for 3.5 billion years. That means that the core must have been cooling down, must have been losing energy, because that energy is
Creates
what is
the field.
required to create the field. Yeah. So we're interested in trying to use these records to give us a tie point for these models to say, if we can say when the inner core nucleated, first formed, then we could say we can rule out all these different models that have that happening at different
Could we
times.
then, Andy, if we could find out when the centre of the Earth started to release these lighter elements and create the magnetic field, if I got that right, that's where it come from, could we then make predictions about when that release of these elements will stop and the field could collapse? There's places without fields, isn't there? There's rocks without magnetic fields out there in the universe. Lad, there's places that don't have fields.
Yes.
Well, I don't know.
No, you're right.
You said that with total authority. There are imagining it. No, there isn't.
You mess around with
nailed
cluster
it, yeah.
algorithms, and I'm going, I know for sure there's no fields on the moon.
Yeah.
What is the one on the
No,
moon? There's
there
one
isn't one on the moon, but there was.
There was, okay.
Right, because
you can-
because the old rocks say that they were magnetized, right? Same with Mars. There's no field there today, but the southern half of the planet is a lot older than the northern half of the planet, and that's all magnetized. So the magnetic field was acting up to about 4 billion years ago on Mars, and then it cut out. Right? Venus does not have a magnetic field today. It's nearly the same, size and presumably a similar composition to the Earth. Why that doesn't have a magnetic field? It's probably because it doesn't have plate tectonics and things. But then through the rest of the solar system, they've all got big magnetic fields. Jupiter, Saturn, Uranus, Neptune.
So you were saying that about Mars. Then this just came to me then. So like we have all these kind of people going about.
Populating Mars.
Like what's the word? Terraforming Mars.
Oh, yeah.
So would
Good
that
game.
then kind of be a pointless endeavour because there is no magnetic field?
No, I wouldn't say it'd be a pointless endeavour. I mean, there's a board game that I really like called Terraforming Mars, by the way. And one of the cards that you can play there is to make a magnetic field. Like that.
Imagine if it was that easy. Bang, fixed.
Yu-Gi-Oh! You weren't expecting my magnetic field. I now have control of this planet.
But then would
It is a little bit
so like
far-fetched,
does that add like a problem then because there wouldn't be a magnetic field essentially? If
I
we
mean,
terraform Mars?
so satellites need extra shielding if there's not a magnetic field to keep them protected from solar wind radiation, right? And this brings us back to what we were talking about earlier. As the magnetic field weakens, if it continues to weaken, then they'll need more and more shielding, right? These satellites, and shielding's pretty expensive to put on satellites, right? Because
I can imagine
there and stuff, yeah.
But I know what you mean. Like when people like Elon talking about terraforming Mars, he seems to make it seem as simple as just dropping nukes at the poles.
That's because it's Elon Musk.
But if you
don't
need a
know.
magnetic field,
He's an engineer, so
I was planning on moving out there, man. And everything.
Well, was he? Got your bags packed.
got me 400 grand. I need to get a ticket on that plane.
So I suppose then a question naturally that came to my mind when I was like doing some initial reading is obviously the climate, right? As we've massively affected it as humans in the past 200-300 years. Has that been the same? Like with the magnetic field and stuff, so have humans. So I know like things happen over very large geological eras. Has there been a noticeable impact from kind of how like we've gone through the Industrial Revolution and how we operate now? Has that affected the magnetic field in any way?
No, I'm pleased to say that's one of the things that we've managed that we'd really struggled to mess up. Actually,
There's still time to ruin it. We can figure something out.
I mean, yes, things would have to go really bad,
wrong.
Yeah, to affect that because it's 2,900 kilometers beneath our feet is the core mantle boundary, and our deepest drill holes are about 10 kilometers or something. So. We're not able to get down there and mess that up.
Mess it
God
up,
for that.
Brilliant news.
Jesus.
I suppose, to imagine, I mean, we're in a bit of the realms of sci-fi, how things could change. But, you know, if we managed to heat up the planet so much that, we stopped plate tectonics somehow, you know, then that would kill
affect
the magnetic field. But,
So I suppose, like you're saying, then the Earth's been cooling since it's forming, since it formed. It's obviously releasing these lighter elements, you know, coming out in volcanoes or whatever you like.
This is just in the core that the light elements are being released. So they just float up to the top of the core, and they might react to the mantle, but they don't.
Top.
They don't. Yeah,
okay.
We don't have any. We don't have volcanoes coming from the deep.
So I was going to say, with the Earth's cooling, but the atmosphere's doing the opposite, isn't it? It's heating up. Like where we're living is getting hotter. So I don't even know what my question is, but it's just a mad like contradiction of like juxtaposition, if you like the core's cooling and the surface is getting hotter, if you like.
So it's a question of timescales, I guess. So this, you know, the energy that's trapped inside the Earth is vast and is being is being released slowly. But, you know, the amount of, I can't remember. I always forget what the power incidence from the sun is, but, you know, it is many, many times more than the power that's released from the interior of the Earth.
Okay.
Right? So in terms of governing our surface temperature, it's all about the sun.
Okay.
And the Earth's heating up because of the greenhouse effect and global warming, which is that then the sun's radiation can't escape us, you know, so it's getting trapped in there. So when that's happening, you know, on a frighteningly short time scale of
the news around that is very troublesome.
Yeah, you know what? I saw a picture on BBC website the other day that was showing sea surface temperature.
I think I've seen this, and it's like down here.
Or
is it the other way around?
No, so there's a bunch of, so it's how it varies through the year, and it sort of it goes, and it normally peaks in March and then declines through the summer, like globally, and it's got all these grey lines for what it's been doing since the 1970s, and just this year
I've seen that.
It's just this red line that's just gone up.
Yeah,
and it's just and it's like, isn't it 5 sigmas of like variation from everyone else, something daft, and everyone's like, oh well, that's not good.
No, you just re-jogged me memory. I seen that, and it's just like the visceral reaction of seeing this rogue line going up,
and it's the loneliness of that line which is so worrying, because it's on its, because it's like, it's not like there's a few up there. It's, well, no, this is on its own.
What was that exactly measuring? Was it surface temperature? Was it
surface temperature? Yeah, because normally it goes up during El Nino, right?
Okay.
Which is when this warm water comes up to the surface in the Pacific, but El Nino's hardly got started. You know, it's barely started. So for sure, as sure as you can be with these things, but we'd certainly expect this to be the first of several years that are well above the average. But if they keep going up like this,
it's not good
news. And, you know, I'm scared it's like a tipping point, right? You know,
well, that's what everyone's been worried about for years, isn't it? And it's like what we had with Dr. Evil Seekman, mathematician, he does like biological modelling. He's like, population models, you have tipping points, and at some point when you get to the tipping point, there's nothing you can do now with the parameters. You go into it's scary, isn't it?
Yeah.
So I suppose then one final question to kind of end on then is, what would be the holy grail of discovery, or is it what you were talking about before?
Well, I'll tell you about, like, you know, my kind of the project, I suppose, that has kept me interested since my PhD, is really to explain magnetic variations over the last few hundreds of millions of years. So what we've seen is, so relatively recent in geological time, So basically, you know, I said that reversals happen on average, 4 times per million years, something. But if you go back 100 million years, there were no reversals at all for like 40 million years. Right, so something caused the magnetic field to be very, very stable in that time period, and since then it's become less and less stable, right, over a period of 100 million years. And then before that, if you go back a bit earlier, back to 160, 170 million years ago, it was reversing like crazy. It was like, it went through this period of hyperactivity where it never seemed to settle down in one polarity almost for a short amount of time. So something has upset the magnetic field and those sorts of timescales. And I like to think of that as being that's magnetic climate change. It's so it's we've got the weather, which is a random stuff, but then you've got these long-term trends happening.
So there's been periods when the poles have shifted a lot, periods when the poles have completely been stable for millions, and then we've got the most recent where we can predict it about
in between.
Yeah.
That's wild. So when we don't have an explanation for that yet, it's presumably related to the convection of the mantle that's over the top, because it's on those sorts of timescales of hundreds of millions of years. Those are the timescales that continents move around on, right? Yeah. And form supercontinents and things, right? So what we think in broad terms is that these continents moving around at the surface, that's all linked to flow in the deep mantle, right? Remember, this is flow of solid rock.
Yeah.
And that's going to be bringing cold stuff down to the base of the mantle, and it's going to be taking hot stuff away from the base of the mantle and bringing it up, right? And that is all going to affect the underlying core, which is generating the magnetic field, right? So if you put cold stuff down, that sucks heat out of the core and gives it extra power, basically. So we've got what we think from our simulations that we're running is that if you put extra power into the core by drawing heat out, then it gets more unstable. It goes a bit wild. So we're trying to link this up. So I've got a big collaboration grant going with 9 institutions. It's led at Cardiff, where they're basically running a load of simulations of flow within Earth's mantle that is constrained by how the continents are moved around, that we think from the geological record, and we're trying to link that and say, okay, well, which of these models, we've got hundreds of models run, which of these produces the changes in the magnetic field that actually match the ones that we observed, right? So that's a really big... That'd
be big.
Yeah, that's a big question that I'm trying to... so it's tying it all together,
I like that.
But for predictability and safety on the planet, we need to find the magnetic field steady state, don't we? Whatever it was doing, whatever the fuck it was doing then millions of years ago.
Let's just redo this.
Yeah.
No, but thank you very much for your time. Thank you very much for coming on. I must say that was genuinely one of the most interesting.
Such an interesting topic.
That was unbelievable.
Every time I speak to someone who does something more interesting, like you speak to some people and you're like, yeah, I'm glad I'm doing what I'm doing. But then you speak to people like you, Andy, and you're like, my research sucks, man. You know what I mean?
I'm sure it doesn't.
I'm in the wrong area.
I'm going to tell your supervisor that.
Sorry, Jenny. On my days. I'm not arsed, lads. Fuck it.
Your research has like immediate, impact and applications, right, in health science and stuff.
It's all a different.
It's all a different
game. So if everyone watching, listening, if you like,
my famous question.
I know we're getting there.
Oh, sorry, lads. Sorry.
Oh my god.
Sorry, I'm eager to ask my question.
Yeah. So if you liked it, hit the like button. If you don't like it, there's a button for that. What do we say, Sam?
The bastards.
Yeah, we don't like you if you don't like it. But keep watching because it gives us views. Now, before we finish, Andy, we have 2 more questions. So we have Sam's famous question and we end on a little question as well. So take it away, Sam, with your famous question.
Right, Andy. This is my question. I crafted this. This took me weeks. Yeah, Ryan said if you don't come up with a good question, you're off the podcast. So I did my work. You're going to die tomorrow, Andy.
Oh, gosh.
You're on your deathbed.
Yeah, you came on the podcast, you were nice and healthy. It's all gone, it's all gone left field.
You're going to die tomorrow, Andy. And a great being comes down. What is the one thing you want to know that you currently don't know that would make that goodbye, that good night a bit more easy for you? It could be something big picture. I want to know this, the world of science, the world of paleomagnetism. Could be something personal, I don't know. It could be...
I'm tempted to be really boring and just say that, that bit that I outlined at the end, that's kind of been my passion, to understand.
That's it.
Yeah, those
that.
changes in the magnetic field. I've had that since, since I started doing my PhD, so
early 20s,
yeah.
So,
early 20s.
So just to finally have that knowledge, I like it.
That would be great to have it nailed down and to know that we could use then the magnetic field to go back further in time and explain things, about the evolution of the planet.
Wow.
Yeah.
I like
that's a good enough answer. I like it.
So the final question we end on. So we ask the question, then we give a little backup one in case the first one's too hard. What is your favourite song of all time? And then the question behind that is, if you can't think of one, what's the one that's like stuck in your head at the minute?
I'm going to say Mersey Paradise by the Stone Roses.
Thank you.
He loves
Yes!
the Stone Roses.
First song, get in. What a tune.
Yes, yeah,
what
yeah.
an absolute
it just
rammer.
takes me back to dancing in like Liverpool nightclubs in the 90s, you know.
Yeah.
Where is it that's got a Stone Roses bar? York.
Has it?
Yeah, it's got a Stone Roses bar, and I was very happy when I was in there.
Yeah.
Because of course I went.
Yeah, you love the Stone Roses.
Did you go see them when they did the reunion tour a few years ago?
I've never seen them. Like,
Never seen
it's
them.
really sad.
I saw them. They was at the Etihad. They were so good, so good.
Really.
Sorry, yeah.
What's the front man called again?
Ian Brown.
Ian Brown, yeah, because everyone
He's
went mad,
funny.
didn't he? Because he done a solo tour about a year ago with no band, and he was just, you know, see the videos that come around on Twitter, and he was just dancing around with like the PAs blasting the music, and people were like, he's probably cheaped out on the tour. He's got no band with him. He's just on his own dancing.
Ian Brown has gone a bit off the rails, like, but he's a funny guy. He's a funny guy.
Lad, with
yeah,
any
so-
hyper creative person, you get the what's it called? The nuances of the
Yeah, you do.
character.
But yeah, so my favourite song so we add them to a playlist. We have like
nice.
the ESI playlist, so we get all the guests that come on, we get them to give us the
that's
tune,
cool.
and we add it. And we used to play it at the end, like end the episode with it, but then because we now use the video, you can't do both, which is it's a bit poo, but we can't. So we put a playlist together instead. So my favourite song added to the playlist, and I'm putting that's it. I'm putting my foot down.
What do you mean?
Of all the songs that we've had so far.
Oh, that was your favourite?
That's my favourite
So you're
song.
going to give another one? I say you've already
Nailed
added
it.
loads to
No.
this playlist. That's your favourite?
Because it's such a good song. Have
Yeah,
you
you
ever
love-
listened to the song?
Yeah, no, many
Mersey
Paradise by
wow,
Stones.
such
but
a tune.
no, I like the Stones. I like them. I like other Manchester bands more. I like I like Oasis more.
I like Oasis.
You can't go wrong with Oasis, obviously.
I like the Smiths more.
The Smiths. They played in John Moore's.
But did he?
Yeah, so this is proper left field. Like, we were talking about Paleomagnetism, and I was talking about the Smiths. So on John Moore's, you know, the Byron Street building down there, the big building. But on the 7th floor, it used to be a student bar. And then before the Smiths got big, they played a gig up in there.
Shut up,
Swear to God.
lads. In that building
Yeah.
there. Jeez.
Yes. How mad's that? Ian, for those who listen, Dr. Ian Malabar, so he runs the Mastermind, and he was telling me.
So you're telling me I sat and learned, like, I don't know, computing.
Linear algebra.
Linear algebra in the room
Where
where
the Smiths belted out.
when
Charming
Morrissey
man.
was belting out his
Yeah, yeah.
tunes. Madness.
But yeah, once again, thank you everyone for listening. Thank you, Andy, for your time. It's been very,
Thank
very,
you very
very,
much,
very
lads.
much
Really enjoyed it.
appreciated.
Thank you
and
very much.
we'll see you in the next one.
See you in the next one, guys. Peace out. Ta-da.